At the end of our last class, we had been talking about TRM, thermoremnant magnetization. We'd mentioned that this is a very stable magnetization, lasts a long time, and can be acquired in little increments as the rock cools beneath the Curie point. We'd also mentioned the fact that the intensity of TRM is thought to be proportional to the intensity of the field in which it is acquired. We actually know that experimentally. Whether we can use that to estimate how strong the magnetic field was in the past is a little bit debatable. We also talked about partial thermal remnants and depositional remnant magnetization, and we said a few words about chemical remnant magnetization, which is the way in which hematite often acquires its magnetization as it forms by oxidizing magnetite. These TRM, DRM and CRM are all, quote, primary magnetizations, and they are acquired when the rock forms. This is a little picture of DRM, and the idea is that the grains all line up with the magnetic field as they become deposited. But as I mentioned, that's a little bit difficult to imagine sometimes, particularly as the grain actually hits the sediment interface. It could easily roll. And so there's a batch of people that say, well, it doesn't get set in until the sediment solidifies. And during that period, just a little bit of jiggling will allow the grains to rotate in the subsurface and thus become aligned with the magnetic field. There are a few other magnetizations that might modify our original remnants of the rock, our primary one. These are sometimes referred to as secondary remnants, and there's a whole bunch of these too. It turns out that squishing the rock can change the magnetization, so you get a pressure remnants. There's a viscous remnants. In fact, we find that the remnants changes over time. In much the same way that you can get dissipation of heat from a substance. There's going to be random fluctuations, which just mean that domain walls can move and magnetic moments can move, and ultimately magnetizations do decay away. It turns out that in some cases, when you have impacts, meteorite impacts, you can get a shock remnant magnetization. And in fact, the lunar geologists have been quite keen on this particular mechanism for some time. There's also what we call an isothermal remnant magnetization, and that's actually the natural remnants we discussed in our last class that can produce a lodestone. It's very strong magnetic fields in nature, and the most obvious one there is a magnetic field produced by a lightning strike. But there are other possibilities too. Now, let's move on at this point to talk a little bit about paleomagnetism. What I've tried to explain in our first couple of classes is the foundation for why rocks become magnetized. But as standard geologists, we're not really interested necessarily in those details, but we might be interested in what the magnetization of rocks can tell us. For example, at what latitude the rock was formed, and therefore by extension at what latitude the locality was at that time. So for example, if we live in Minnesota and we look at some 200 million year old rocks, we might want to know at what latitude Minnesota was at that date. Actually, there are not very many 200 million year old rocks around here, but never mind. Okay, so that brings us to paleomagnetism. We want to use that primary remnants to find out something about what's going on. And we might be able to see if that particular piece of crust has drifted around or rotated since the formation of that rock. And so this is sort of leading us into proving continental drift, as it were. And all we really have to do is to imagine that the magnetization is somehow frozen in when the rock was formed. And if there are some problems with shock remnants, we'll rely upon the rock magnetic people to tell us about that. So the most obvious example of this is indeed continental drift. And here are the continents, 180 million years ago, and as you can see, North America over here is attached to Africa and Europe, and Great Britain and Newfoundland were much, much closer. Flying across the Atlantic was a lot less expensive, although probably there weren't very many flights. And this standard interpretation that all geologists learn about in their Intro to Geology class is all based upon paleomagnetism. So how do we do this? Well, here's our continent down here, and here we've got a rock that's being magnetized a long time ago. Let's say 200 million years ago. And of course it's pointing north. But as that continent starts to move and rotate, no longer is that magnetization pointing to the North Pole any longer. All right? And so as time goes by, it starts giving us a more aberrant result. It's pointing to a different place on the Earth's surface. That different place is, and I don't want to anthropomorphize too much here, but it's where the rock thinks north is. The rock is misled because the continent it's embedded in has moved, but the place it's pointing to is no longer the true North Pole. It's a different position represented by the blue dot. It's called a virtual geomagnetic pole. And we folks in Paleomag refer to this as a VGP, because naturally we want to reduce everything to initials. So the blue point is the VGP. This is the North Pole right here, and the fact that they are different we interpret as meaning that the continent has drifted. Now, the angle between the two directions, the direction of true north and the direction of the VGP, is sometimes referred to as the magnetic declination. Okay? And the distance away that the VGP is, that will change over time as well. Now, this distance from the North Pole to where you are on the Earth's surface is what's referred to as the colatitude. Latitude is obviously the distance from 0 degrees, whereas the colatitude is 90 minus that, the distance from the pole. Now, on this arc, that's now called the magnetic colatitude. All right? So I'm just establishing some terms here. So here's a picture that I pinched from the internet, and you can see that the North Pole's here. Here we are in South America. That's the direction of north, and the black line is the true colatitude. But South America has drifted, and so it's rotated such to give the rock's magnetization a declination D, and the red line is now the magnetic colatitude of this VGP. That's the place on the surface of the Earth that our rock's magnetization is now pointing to. Now, that magnetic colatitude is the distance from the North Pole, and it turns out that we can actually calculate that quite simply because of the shape of the Earth's magnetic field. Now, the shape of the Earth's magnetic field is actually quite complicated, as we'll see later. But initially, it kind of looks like a bar magnet at the centre of the Earth. And bar magnets have a very predictable magnetic field shape that look like a couple of Mickey Mouse ears here on either side of the Earth. And you'll notice that the magnetic field lines are vertical at the poles, and they curve around and come in at different angles as you go around the Earth. So at the equator, the magnetic field lines are nearly parallel to the Earth's surface. That means that a rock forming at the equator has a magnetic inclination. That's the angle of the magnetization down from horizontal. The magnetic inclination is 0 at the equator. It gets steeper and steeper and steeper at 45 degrees north, this inclination is about 63 degrees. And when you get to the North Pole, that inclination becomes 90. In fact, that's one way you can find when you're at the North Pole. If you ask little kids to say what happens to your compass at the North Pole, they all say, oh, well, it'll just kind of go around. They don't really have an answer for it. That's because they don't understand that third dimension. In actual fact, if you have a compass that is arranged such that it can depart from being horizontal, it will end up being vertical at the North Magnetic Pole. Now, and be careful there, because there's a difference between the North Geographic Pole and the North Magnetic Pole. All right? So, if we assume that the Earth's magnetic field is that of a, quote, dipole, like a bar magnet, one north, one south, then that inclination can tell us how far we are away from the North Pole. If the inclination's at 90, we're at the North Pole. If the inclination is plus 63, turns out we're actually 45 degrees from the North Pole. If the inclination is 0, we are 90 degrees away from the North Pole. And if the inclination is minus 90, we're at the South Pole, 180 degrees away from the North Pole. In actual fact, we have a little equation for this. It's called the dipole equation. And I've got it written down here. The tangent of I is equal to twice the cotangent of P, where P is that magnetic co-latitude. Well, if you play around with a bit of trig, we happen to know that the co-latitude minus 90 is the latitude. And we know the relationship between cotangent and tangent. We can simplify this whole equation down to this. The tangent of the inclination is twice the tangent of the latitude. Hey, great. So if you measure a rock and you find out its inclination is 0, then guess what? the latitude has to be 0. And it's a very simple way of finding the latitude at which your rock formed. So if you're looking at a desert sandstone, you might expect the latitude to be like 20 degrees or something. Whereas if you're looking at a glacial rock, maybe the latitude would be 70 degrees. And so we can find out the latitude at which rocks form and put them together with the other information we understand about the rock, so as our story of the geological history makes sense. And that is one of the most important things to a geologist trying to come up with the geological history of an area. And they'll send their rock away and find out the co-latitude, like this. There are actually, as I said, compasses that have been built that allow us to find out that inclination. And this is one of them, which was made in 1908. And it's got 3 feet, you level it, and you can read off the inclination of the magnetic field very easily from an instrument like this. That pattern is shown on the left-hand side of your image here. This is a cross-section of the Earth, and it's showing you the direction in which the dipole field points. Upwards at the South Pole, downwards at the North Pole, and parallel to the surface here at the equator. And the angle changes. We define these inclinations as being positive, and we define these inclinations as being negative. All right? So a negative inclination is a measurement that you would make of a magnetization that points up, away from the surface of the Earth, and a positive inclination points down into the Earth. And for the dipole field, positive in the northern hemisphere, negative in the southern hemisphere. Now, this little observation was used quite early on in the history of paleomagnetism to come up with a fabulous demonstration of continental drift. And it was done in India on a bunch of lava flows called the Deccan Traps. And when they were first sampled, everybody noticed that it had a negative inclination, represented by this blue arrow here. But quite clearly, at the latitude of Bombay, it should have had a positive inclination. So kind of puzzling. How can we have the magnetization of the rocks be so different from the direction of the Earth's magnetic field? Now, one possibility is the Earth's magnetic field has varied. In actual fact, we now understand it was because of continental drift. And at the time those rocks were formed, the Jurassic, India was in the southern hemisphere, and here's the magnetization of the rocks being acquired parallel to the magnetic field in the southern hemisphere. Once we had got that, then the prediction is that if we look at rocks of intermediate ages, they will give us intermediate latitudes. And sure enough, the Deccan traps gave us India being here in the Jurassic. Other rocks indicate that it was here in the Cretaceous. Still other rocks give us an early tertiary position of here and a mid-tertiary position here. And it's only now that Bombay is where it is in the northern hemisphere. And this demonstrated that India drifted north very significantly since the Jurassic. I always tell my intro kids that it was speeding along like a Ferrari. Really was going quite fast. So here's a little animation that was put together to show the different places of India going from about 70 million years ago to zero. So we haven't got the full 200 million years in here, but you can see the way that the Indian subcontinent moved. And ultimately, obviously, here, it's colliding with Asia. And that, of course, is the observation that led us to thinking that maybe the Himalayas were produced by this collision.